Mm, Good evening, dear professor, dear teachers, and dear respective teaching assistants, and my dear friends. So, today I'll be presenting my research paper topic, and that is like pixel level and semantic level adjustable super resolution, which is a dual LoRa based approach. And this paper has been recently accepted at CVPR 2025. And the thing is that this paper has been done by the authors Lingchen Xuan, Rongyuan Wu, Zhuan Ma, Songchen Liu, and Qiaosi Yi and Li Zhang. And it has been funded by OPPO Research Institute and it has been co-supported by the Hong Kong Polytechnic University. So me being a student from IIT Jodhpur, on their behalf, I'll be presenting this entire paper. And for my final major examination, where it is also supervised by Dr. Mayank Vats, under his supervision, I'll be presenting this entire paper. And without much ado, let's go through it. So first we'll be getting through the content. Like, let's see what the content is. The first thing is that we'll be going through introduction, the challenges, the model formulation, the solution, optimizing for semantics, the inference process, experimental setup, quantitative comparison with the state of the art work state of the art works, then qualitative results as well as user study. Okay, with conclusion followed by vote of thanks. So first, hello everyone. I am presenting a paper that is PiSA SR. So here we have developed a new super resolution method that addresses a major limitation in current diffusion-based models, and the inability to balance pixel fidelity with semantic creativity, where we have find our approach that is our PiSA SR, and we introduce a dual LoRa architecture that allows us and the user, at the same time, to adjust these two objectives independently without retraining. So here we can see the fundamental challenge in super resolution is that there is always a trade-off between fidelity and perception. So if we focus on pixel accuracy, we get blurry results, right? We get blurry results. But if we focus on generating, if we focus on generative details, we might create artifacts. So as we all can see in this grid, the existing methods usually land on just one spot. But our goal was to build a model that spans this entire grid, allowing users to choose whether they want to prioritize denoising or texture generation. Going through pixel level, enhancement, or they want to go through semantic level enhancement, right? So to make this efficient, we moved away from expensive multi-step diffusion, as shown in this figure. We formulate the problem as residual learning in a single step. We teach the model to predict the difference. The residual between the low quality input and the high quality output. This not only makes our model faster, but also mathematically it allows us to scale this residual, later, to control the output strength. So it accelerates convergence and also allows us to introduce scaling factors, that is lambda, for generation enhancement, right? So the solution, the core of our methodology is this dual LoRa approach. Instead of training, on the entire one giant network, we insert two lightweight adapters into stable diffusion. And first we train the pixel LoRa, the pixel level stuff. So there we strictly clean up the image using simple L2 loss. Then we freeze that, and again we train the semantic LoRa, as we see here in stage 2, to hallucinate fine details, right? By training them sequentially and separately, we prevent the objectives from conflicting with each other, right? So optimizing for semantics, we also see, like, why only CSD loss, right? Why only CSD loss? The answer is, like, to get those high quality details, we utilize this CSD, classifier score distillation, as shown in this figure. While L2 loss, it removes noise, it leaves the texture flat. Whereas CSD, it leverages the knowledge inside stable diffusion to generate realistic, textures like the feathers on this bird. And at the same time, we chose CSD over other methods because it is far, by far much more, memory efficient and stable towards training. And apart from that, in the inference process also, we can see, like, here's like where the magic happens for the user, because we separated the training. We can combine the modules dynamically during inference. But using this equation, as we can see, the adjustment equation, we treat the output of the semantic LoRa as residual that we can scale up or scale down. And by adjusting these lambda values, user can dial in exactly how much noise reduction or how much texture generation they want for a specific image, right? So user can tailor the I mean the output style instantly. So that is what it makes this thing much more standing out. And apart from that, we built our model on stable diffusion 2.1 and trained it on standard datasets like LSDIR. We tested it extensively on both synthetic as well as real world low quality images. Crucially, also we used a wide range of metrics, not just PSNR, or I mean PSNR for accuracy, but also reference free matrices like a clip QA and music, right? To truly measure how good the image looks to the human eye. And this can be further confirmed from this table, as I have put it over here. And apart from that, we also see, like in this slide, that quantitatively, PiSA SR, it outperforms other state of the art method, like the existing methods, as shown in this table too. We also achieve the highest scores in perceptual matrices like clip Q and music, compared to stable SR, like which takes 10 seconds. Our one step approach is vastly much more efficient and it delivers superior quality. And apart from that, in this slide, with qualitative result and user study that we have done, we can see that like what to say, like visually also we can see the difference is clear. Just look at this example in figure 8. Figure 5 and figure 8. Like we can see this method leaves it unreadable, but like figure other methods, it completely leaves it unreadable, right? But the bird's nest one, that as we can see in this figure. But our PiSA is SR. It restores the characters bird's nest accurately. In the penguin example, also we can see we recover the fluffiness of the feathers that others smooths out. We also conducted a user study where 98% of the participants, preferred our semantically enhanced results, confirming that adjustable guidance, it aligns with human perception, right? And apart from that, in slide 10, to the last slide, where we would like to go with the conclusion, and the conclusion is that PiSA SR offers a flexible, efficient solution, to super resolution problem, by not just simply training and all those process, but by decoupling the entire learning process. And we have successfully provided a tool that doesn't just guess the pixels as it is, but rather it lets us decide how the final image should be, right? So we believe that this is the future of real world image generation. And thank you for your time, and I invite you to check out our code on GitHub. Code on GitHub. That's it. Okay, thanks. So that's it, and thanks. I invite all of you to go through our GitHub code and provide the suggestion, infer it, run, or whatsoever. Right? Thank you a lot. And if you guys have any question, feel free to comment it out or send me out my personal mail address, in my personal mail address, or DM me, or mail me. That's it, right? Thank you.